Hi everybody, thanks for coming to my talk called Acceleration-Based Quadrotor Guidance Under Time Delays Using Deep Reinforcement Learning. So the main topic of this presentation is deep reinforcement learning. It's an artificial intelligence technique where an agent learns how to solve a behavior entirely on its own through trial and error. So this is what a sort of a system would look like. We have an observation O of t that comes into this deep reinforcement learning block, sometimes called an agent. The agent calculates a control effort, U of t, that goes to dynamics. The dynamics gets stepped forward in time and returns a new observation to the agent. But the dynamics also returns a reward signal, R of t, to the reinforcement learning block, and that reward signal is what the reinforcement learning uses to try and tweak its outputs. So it looks at all of the input observations it's seen, all of the control efforts that it's calculated, and then what the rewards are that have resulted from those control efforts in those states. And it tries to maximize the amount of rewards it receives by intelligently choosing the proper actions to take. And over time, through trial and error, the deep reinforcement learning agent can master a task. And this has been applied to a number of scenarios. So the game of chess, for example, where a reward of +1 is given when the agent wins the game, a reward of -1 when it loses the game, and 0 for every move that it takes. And letting this train for a long time has led to the most powerful chess engine in existence. So my research is to try and apply this to quadrotors to solve difficult problems. So I'm not the first to do this, though. Others have done quadrotor reinforcement learning work for guidance. And in 2015, a maze was discretized into a set of nodes. And using reinforcement learning, each node was given a value. And then to solve the maze, the quadrotor just had to follow the nodes that had the highest value, and it would solve the maze. In 2019, a discrete set of motions for a quadrotor were chosen or were designed. So it could maybe move forward, move left, move right, or stand still. And then using a vision camera and deep reinforcement learning, a quadrotor had to decide which action to take based off of its observation. Last year at this conference, we presented continuous solutions. So whereas those two previous ones were discrete, we're proposing a continuous velocity-based deep guidance approach where a velocity signal is commanded or is signaled from the deep reinforcement learning, which some sort of onboard controller will try and track. So this is what that system looks like. Instead of having the deep reinforcement learning do guidance and control all together, we restrict it to only do the guidance portion, and then it commands some velocity signal, which is tracked by a controller, and then the controller executes a control effort on the dynamics. And the reward signal is used just to train the guidance. So we call this approach deep guidance, and we commanded velocity signals. So in this work, instead of commanding velocity signals, we are commanding accelerations. And the purpose of this work is to compare whether acceleration-based deep guidance is better than velocity-based. So the contributions from this work are the acceleration-based deep guidance technique, applying the deep guidance technique to quadrotors, and some experimental validation. All right, so we'll start off with some numerical simulations. We've got how to design a task for the quadrotors to solve. So we have two quadrotors here, a target and a chaser. The chaser starts at some location and has to move to this tracking point, we call it. It's a point that's offset from the target, and the target's not moving. So while this is a relatively simple task and can be completed with regular guidance and control approaches available today, I'm using this as a testing ground to compare the velocity and acceleration-based deep guidance approaches. So the reward function that we used is a simple reward where positive rewards are given if the chaser moves closer to the desired location, and a negative reward is given if it moves farther away. For the velocity based deep guidance, we had to also apply a penalty for high velocities near the desired location, which I'll discuss more later. The learning algorithm used is the D4PG algorithm because it's continuous and deterministic, and all the details of that are in the paper. And the dynamics, we're not modeling a quadrotor in dynamics, I'm just modeling a double integrator cube. And this kind of shows that the model needed to train within does not have to be identical to the model that's experienced in real life. And that's one of the benefits of the deep guidance technique. So here's some simulation results. Here's the velocity-based guidance results first. There are 4 trials here where the red chaser has to move to that desired location, and you notice that there's quite a bit of overshoot, and then there's also some steady-state offset, especially in the last one here. You'll notice it. But overall, it does solve the task. When we compare that to the acceleration-based deep guidance results, you see that there is very low overshoot and similarly steady-state offset. So off the bat, we see that the acceleration-based deep guidance appears to be best. And if I look at a time series plot showing the position error versus time, the acceleration curve is shown in red, and you see that it goes to 0 and stays there, whereas the velocity one oscillates a bit and then has some steady-state offset. The steady-state error is a result of the reward function. I added an extra term into the reward function for the velocity model to try and prevent overshoots. And the way I did that was I penalized high velocities near the desired location, so that would hopefully approach the desired location with a low velocity. But what ended up happening is it did reduce the overshoots, but then it introduced some steady-state error because it may receive penalties for using velocity to get to the desired location. So it was I found the best solution was to stay a bit away from the desired location. So now that those 2 tasks were trained in simulation, it was time to deploy them to an experiment. Here I have the observation being fed into the deep guidance block. The deep guidance block is just copied from the simulation and brought to the experiment. It can output an acceleration signal or a velocity signal, and then that's fed to the controller that we have in the experiment, and then the experimental dynamics. So I'm comparing both the acceleration and the velocity deep guidance approaches in experiment as well. These are the quadrotors that we're using. They're called Explorer, and they were developed in-house at École Nationale de l'Aviation Civile in Toulouse, France. And they fly around in this flight arena. It's a 10 meter by 10 meter arena with 9 meter height. And here's some experimental results. The velocity experiment. So we have the chaser that takes off on the right, the target that takes off on the left. Then the chaser has to move to that desired location in front of the target. This is sped up quite a bit. And it does that successfully. But then we take it a step farther, we move the target around a bit, and we see how the chaser follows it. So this is a task that wasn't seen during training, but it can still accomplish it in the experiment here. Though we do notice there's a lot of overshoot and some steady state offset, especially for that velocity model. Then the acceleration model, see there's quite a bit less overshoot and steady state offset. There's a bit of jumping around due to some sensor noise that we had. But overall it does quite a bit better than the velocity approach. And then a time series comparison. Red is acceleration, black is velocity. The position error versus time. We see that the acceleration one is less than the velocity for pretty much all time, even when the target was moved. So just as an extra test, we tried deploying this to a different vehicle. This is a hexacopter you can see on the right. And so a totally different vehicle that wasn't seen before. And the acceleration-based deep guidance model performs that task well. So conclude, the acceleration-based deep guidance model is better than the velocity-based one. It had better performance and enabled a simpler reward function. And deep guidance is appropriate for quadrotors. So future work, we're going to apply this to more difficult tasks. And thanks for listening. All the code is open sourced on GitHub if you'd like to see it. And you're welcome to email me or ask any questions. Thank you.